Zoeb, shuru kare? Okay. Right, so this is lecture 4, and today we are going to talk about the covariant derivative. Then we will go on to talk about curvature, and in this way we will begin our understanding of curved manifolds. But before that, let me remind you that when we talk about vectors, that vector V actually has a physical existence. So in fact, this is what Riemann insisted on. He said, look, you can always write a vector in this way. There's V mu, E mu. E mu are the basis vectors. Any vector can be written like this. People say the normal use of the word is that V mu is a vector. That's not true. It is this. And so you can view this from some other point of view. You can view it from here, there, wherever, but the vector V has a physical meaning. So it's actually something which is present in space. From this, we will make tensors of various kinds and so forth. But now I want to tell you once again that this E mu is to be thought of as fixed basis vectors only when the surface is flat, that is on a flat manifold, zero curvature manifold, not otherwise. Normally, this will change. Yes? You need to. Can you come a little bit up front? Okay.
Achha sir, simple question. With the V, you have the mu in the superscript, and then with the basis vector, you have it in the subscript.
Yes.
Is there like a reason for that, or is that just conventional?
Yes. Let's take this as the convention. We could have done it the other way around, but we're going to do this. And this E mu, we're going to say this is d by dx mu. That is to say, this is the vector in the direction of increasing x mu. And just to be absolutely clear, I'm going to show you what this means on the tangent plane. So you know what the tangent plane is. Zoeb laga do. You know what the tangent plane is. It's the plane which is spanned by all tangent vectors at one given point P. And because I have such a beautiful picture of this, which I made in Mathematica, you can see that at this point, Zoeb, इसको सिर्फ ये दिखाओ, मुझे ना दिखाओ. Just show this. Okay. So, in the direction of increasing phi, you have E phi. In the direction of increasing theta, you have d theta, which is E theta. And you see that there are two tangent planes shown in this picture. One which is above and one which is below. And even though we have E phi denoted at both points, these E phi's are different vectors. The E thetas are different vectors. Even if we call them d by d theta or d by d phi, the point is that basis vectors change as you move along the manifold. So this is just to make sure that you have exactly the same picture as I have in my mind. So what we're going to do today is look at a vector which is on a tangent plane, and then look at a vector which is at a slightly different point. You know that there are as many tangent planes as there are points on the manifold. That is to say, there are an infinite number of them. Okay, so that's the only picture I'm going to show you. When we have a vector on the tangent plane, sorry, lights, then of course we can have another vector W, which is W mu E mu. Then we can also define a dot product between them. And we define it as follows. It is G mu nu V mu W nu. And why do we define it this way? Well, because we are inspired by this thing which we wrote down at the very beginning, that the separation between 2 points is this. And so that leads us to this definition. So
you have W nu instead of nu?
no, this is mu, nu.
No, in the equation where you define W.
Here? Yeah, but this is a dummy index, so you can call mu, nu, you can call it anything, it doesn't matter. But if for clarity you would like that, it's all right. Dummy indices will be renamed again and again, and there's a whole game.
Different directional derivative.
No, this is not. This is an actual physical object. This is an actual physical object which is the same as this only if V and W are the same. Only if V mu and W nu or W mu are the same. So there's V1, 2, 3, 4 up till n, W1, 2, 3, 4 up till n. The two vectors are the same only if all the V's and all the W's are the same. And it does not make a difference whether I call this nu or rho or whatever. It's a Einstein summation convention index. Okay, so is this okay as a definition? See, there's the 3 lines of it. Is this okay as a definition? Yeah, because what does a dot product have to satisfy when we do it in ordinary Rn, ordinary space? You have to have V dot W is equal to W dot V. Okay, is that satisfied over here? Yes, because I can just rename mu as nu and nu as mu, and so then I can switch and I get V dot W is equal to W dot V. What else should it satisfy? That there should be linearity. So if I take AV plus BW dot CZ, then this should be equal to C into A V dot Z plus C into B W dot Z. And obviously it does, because if you just put this over here, and this is obviously true. So the linearity property holds as well over here. So that's also okay. And so this is a good definition. Right, so proceeding from this, suppose we take unit vectors. AC chalana. Then E mu dot E nu. Well, that's equal to G mu nu. And so you could say that the definite darwaza band karo. Then you could say that the definition of G mu nu, so this set of numbers is the dot product of the two basis vectors. Right. So now we have both a rule for adding vectors at the tangent plane. Only at the tangent plane, nowhere else. Why can we not add a vector, a tangent vector at the point P and a tangent vector at the point Q? Because their basis vectors are different. We don't know how to, we know how to add vectors on the tangent plane only. We know how to take dot products of vectors which are on the tangent plane, but not anywhere else. I can't take an arbitrary vector at this point on the tangent, on this point on the manifold, and at this point on the manifold. I don't know what the dot product is. I don't know how to add them. And so we are very limited to the vectors on the tangent plane. But then I can't always stay on the tangent plane. I can move to a point close by. So what I want to do now is calculate what happens when I move, let's say d by ds of a vector v. Well, this is then, oh no, I want to move, I want to do this. I want to move to another point on the manifold, and I want to know what is the partial derivative so I know what V is on my tangent plane, and I'm moving to a different tangent plane now. Okay, so let's work it out. This is V mu. I can't use the word, I can't use this, so let me call this mu. All right, but this has two parts now. And there is, by the chain rule, this thing also there. Yeah, and if the basis vector does not change as I go to a nearby point, that means the basis vector is a constant and we are in flat space. But now we are allowing for the fact that the basis vector can also change. Yeah?
सर जो हमारे पास टेंजेंट स्पेस प्लेन है, एक पॉइंट पे हमने जो टेंजेंट प्लेन बनाया है, अब उस प्लेन में डिफरेंट पॉइंट्स होंगे ना, तो क्या एक टेंजेंट प्लेन पे हम कोई भी पॉइंट लें तो उनके लिए ये ई म्यू और ई न्यू बराबर होगा?
टेंजेंट प्लेन में एक ही पॉइंट है जहां द टेंजेंट
प्लेन में तो डिफरेंट पॉइंट्स होते हैं ना हमारे पास.
अ प्लेन ऑफ कोर्स
टेंजेंट पॉइंट क्यों नहीं बोल रहे, फिर हम उसको टेंजेंट प्लेन क्यों बोल रहे हैं?
Okay, so your question is that there are lots of points on the tangent plane, but there's only one point that hits the manifold. That is where we calculated, that is where we defined the basis vector. Okay, now you can make any other vector by taking a linear combination like this. So the plane, in fact, you could say is defined by the total set of vectors that you can add together. Now, the two vectors that I talked about, which were added together or whose dot product was taken together, all those vectors were on the same tangent plane.
Okay, sir.
Now I'm going to a different tangent plane, one which is separated by a small amount dx mu, is only a little bit away from the point P. So it's the point P prime, and P prime is very close to P. Okay. So now we have this, which is what we are used to in ordinary mechanics, in all the vector calculus that you have learned, but this is different, and now we will have to calculate this. So how to find dE nu by dx mu? And this is going to take some effort, but it's going to be absolutely crucial.
ये जो लास्ट टर्म है ये तब नहीं हम ऐसे निकालते जब लेट्स से हम कार्टेशियन से सिलिंड्रिकल में जा रहे होते हैं तो वो बेसिस वेक्टर का जब डेरिवेटिव लेते हैं सो लाइक द पोजीशन इन टर्म्स ऑफ स्फेरिकल कोऑर्डिनेट्स पे जब उसको हम वेलोसिटी फाइंड करते हैं स्फेरिकल कोऑर्डिनेट्स में तो हम इसी तरह का डेरिवेटिव नहीं लेते.
Yeah, but polar coordinates, when you use them, then you're using, if you take fixed r, then you're on a curved surface. And E theta, E phi will be different at different points on the manifold of the sphere. Okay, so how should we find that? And now this is going to take us, this is going to take some effort. It will not be trivial, but it will be not too difficult. Okay, so let me start with the definition of, let's say, this was, what did we call it? E mu dot E rho. And let me take the d by d x nu of this. Of both sides. And I'm going to write d by dx nu always as d nu. It's the same thing, but you know, it's nicer to write it this way. All right, so then we have d nu g nu rho equals so now here I will have to use the chain rule. Dot E rho, and then E mu dot, yeah, d nu, so wait, this is d nu of E mu dot E rho. I need that chalk. ठीक. And so this is going to give me two terms, d nu E mu dot E rho plus E mu d rho dot E nu. Okay. D nu will act on E mu dot E rho, and then E mu will remain as it is, d nu yeah, right. Okay, and I can now do the others, but let's come back over here. This I need to look at some general features of this. So, what is this going to give me? It's going to give me a vector in the tangent plane at the point P. I don't know what vector, but it's going to give me some vector in the tangent plane at the point P. So, dE nu by dx mu is going to be a linear combination of the E mu's. Okay? Why? Because it's going to be a vector, and a vector is then going to be just a linear combination of other vectors. So that's point one. The other thing is that, recall that E nu is d by dx nu. And if I take d by dx mu and d by dx nu, well, the two commute with each other. I can take nu first and mu later, which means that dE nu by dx mu must be the same as dE mu by dx mu. They're exactly the same. Hence, whatever this is, I don't know what this is, but whatever it is, it's got to be symmetric in mu and nu, and it's got to be a linear combination of basis vectors. Hence, dE nu by dx mu is going to be, maybe it's better I write it d mu d mu E nu. This is going to be symmetric in mu and nu, and is going to be a linear combination. So let me call this something which is symmetric in mu and nu, and which is a linear combination of the vectors here. So this is my assumption, and the question is then, what is C mu nu equal to? And this is now what we are proceeding to find. Okay. So look at this over here. Then this is, what should I write? So for this and this, I'll write C mu nu. And since I cannot use rho again, I'm going to say this is E sigma dot E rho. And then here, plus E mu. And here it'll be C nu. So C nu rho, and something over here, sigma again. Right. Okay, so what does this give us? C sigma nu mu. This is G sigma rho. And this is G mu sigma. Because by definition, this is equal to this, and E mu dot E sigma is equal to this. Okay? I'm going to rub this out. And now I'm going to make a cyclic permutation. So mu nu rho, I will run the cycle so that this is rho mu nu, and I'm going to write these. I'll write this so that it becomes easier for us to. So d mu nu g mu rho is equal to this. All right, so now you'll have to help me rotate this. So when I rotate, mu becomes rho, rho becomes nu, and nu becomes mu. Nu is mu, mu is rho, sigma is sigma, rho is nu, plus so that's a second equation. Let me take a third one. So rotate this again, nu rho mu. So this becomes rho, rho becomes nu, nu becomes mu. And so mu becomes rho, and rho becomes nu, g sigma, nu becomes mu. Okay, good. See, all this is simply recycling the indices, nothing profound over here. Now I'm going to do this. I'm going to add the first and the second. And I'm going to subtract the third. And let's see what we get. Okay, so new, yeah. There's mu over here. Or let's see, what did we have? D mu, g rho nu. Yes. So add the first two, subtract the third. Okay, let's see what we get. So plus G sigma. You know, this becomes quite boring writing all the indices, but this is still, this is what you have to do. If you have to do it, you have to do it. And this last term, thankfully, no more writing after this. And if luck is good, then we shall see some cancellation. Huh? Sigma mu nu. Wait, here? Yes, this over here, so sigma rho nu g sigma mu. Yeah. Do you see any cancellations? And what? Last term was rho mu. The last term was sigma rho mu g rho nu sigma. Right. Yes. Okay, but we see there's good news. This is cancelling with that. Why? Because C rho nu and C nu rho are the same, and G is symmetric. Hence, this cancels that. Let's look at this one. And you see, exactly the same over here. And what about this? This is C sigma nu mu. This is C sigma mu nu. And this is, so this is equal to therefore, we have found that 2 sigma mu nu into G sigma rho is equal to or let me take the 2 away over here, write this as half. Aha, this is now looking very interesting, isn't it? Okay. Now I need actually not this thing over here, but I need C. So what should I do? Multiply by the inverse matrix, exactly. So let me multiply by what? By it has rho. I don't like lambda. So how about gamma? Okay. What is up above over here? And then since rho is being summed over, so G rho gamma into G sigma rho, this will give us delta gamma sigma. So wherever there is a sigma, you put a gamma. And hence we get C gamma mu nu is equal to half d mu G gamma nu d mu Ah, beautiful. What is this? That's the Christoffel symbol. So, if you like, what I will do is I will simply rub out the gamma and put sigma instead of gamma, because that's what we are used to. So in this, I am now going to, oh yes, oh yeah, let's do that. So C gamma mu nu is equal to half gamma rho into this.
Then we have to write every gamma in the bracket as well. So not the row over that side.
Let's see. I rho gamma.
जो आपने पहली term लिखी है d mu g gamma.
Yeah. So we are summing over gamma. So this will be rho here. Yeah. Yeah. Let's check that everything is working. So we are summing over gamma here, here, here. Mu nu is here, and you can see that this is symmetric in mu and nu, obviously, because you exchange mu and nu here, you get this, and g mu nu is symmetric over there. And so, well, look, that's a non-trivial result. That says d mu e nu is equal to, is the same as the Christoffel symbol. That's how the basis vectors are changing. As you go from one point to the other, then the two parts of the vector that are changing, one are the components, the other are the basis vectors. And we've calculated now how the basis vectors have transformed, and such a beautiful result. So then this tells us how the vector actually transforms as you move along a curve. This leads to a definition of what is called the covariant derivative. So the covariant derivative d mu of a vector component nu, v is, so remember this, what this v nu was, when we take a vector v and we expand it, these are the components, and what are the basis vectors? E nu. So this is by definition let's call it and let's see, E, yeah, is that correct? And no, yeah, that's okay. Yeah, one index is
row on a side, twice.
now it's correct. Yeah. No, but yeah.
Now new is missing.
And now new is missing. So this is the way to remember it. You see, nothing. There is mu down over here, mu down over here. New has to be on top over here. Can be on top over here. It cannot be on top over here. And it cannot be on top over here because that would simply multiply. So this is the correct definition.
Yes, sir. That's what is missing.
सर एक बेसिस वेक्टर भी मिसिंग है अगर हम उसको कॉमन ले लें तो ये ठीक है
Wait, I should. You have the notes? It's okay. We'll fix it in a while.
सर एक्चुअली ये जो लेफ्ट साइड पे जो वेक्टर है उस पे इंडेक्स नहीं है क्योंकि ये
किस पे इंडेक्स नहीं है?
ये जो लेफ्ट साइड पे जो v है उस पे इंडेक्स नहीं है क्योंकि ये v कैपिटल v है
No. I'm only looking at how this component is changing. Then there's E sigma is gone. Yeah, that's all. Yeah, that's all. There's no sigma over there. This is by definition then. So then this is the part. This is the usual part in flat space. In flat space, this will be 0 because the gammas are the derivatives of the g's. So this will be 0 there. So that reduces to the normal, and now we have all the indices also completely matched. Okay. What was the equation for the shortest path, for the geodesic? You remember that? X rho double dot plus gamma rho mu nu right? That was the differential equation, second order differential equation you must solve in order to find the geodesic. Okay, and what were these things over here? X dot mu was dx mu by d lambda or ds or whatever affine parameter there was. Now I am going to talk about parallel transport of a vector. Okay, so suppose you know, we were talking about geodesics, and I said think of it as a car that you are driving, and if you don't move your steering wheel, then the vector in front of you is constant. So what we need to do now is take that vector and move it along. What does that mean? It means you calculate the derivative of that vector. So let's say we are moving along a geodesic and have a vector that points along that path, along that geodesic. What is that vector called? We've given it a name. What did we call it? Tangent vector, exactly. So x mu dot is a tangent vector. There are lots of vectors that pass through the point P, but only one vector which points, which is in the direction of motion, and that's the tangent vector. Okay, so I need to calculate the covariant derivative with respect to what? What do I need to calculate it with respect to? How much I've moved along the path? And what is the thing that is changing along the path? The parameter. And the parameter that we are using is S. So actually, I need to calculate this. Okay. Look, at a single point, you can have many derivatives. What is a derivative? You take the value of the vector here, or the value of a function here, and then take the difference of the two, divide by the whatever distance there is, or whatever difference in parameters there is. That's how you define a derivative always. So it's my definition. Here we're differentiating with respect to S. So this is d by ds, and here and then here we are told that we have to multiply by this and this because the basis vectors are changing. Okay. And so V rho is and there's gamma mu rho, and then this vector here, x. Okay, so this is wait, this has to be linked with this. So mu तो आ गया ना, and this over here has to be linked to this. क्रिस्टोफल के ऊपर जो है, that has to be mu. Then I have, and then, and so there has to be a mu over here. And this, so, and this, so I should take over here rho. Okay. So if I take rho over here, there is rho over here, which means that here there should be, no, that's the, I should have rho over here, and then this sigma, whatever, yeah. And then rename this sigma as nu, okay. Now let's see if this makes sense. So, no, this,
First becomes x dot rho. First term, second line.
This, if I take rho over here, this has got to be rho, okay, and this is then rho. Okay, so we've used the rule of the covariant derivative as is given over here, and we get that, which we know is 0 for a geodesic. And hence, this thing is 0. That means that if I take a tangent vector and I move along the geodesic, then it will remain constant. Highly non-trivial result. And then this gives us a definition of how we are to transport vectors in general. What do you think should be that definition? So, what is parallel transport? We want the vector not to change. Of course, components could change, but we want the vector not to change. So, how should we define parallel transport? So then, if you won't give me a definition, I'll give you a definition. You want to give me a definition? I want to know how I should define parallel transport on a curved surface. What does parallel, in normal life, what does parallel mean? That you're taking something and just translating it without changing it. So a vector will be transported from here to here without change. That, by definition, makes them parallel. Okay, now we are on a curved surface, and I want to know what would be the definition. Yes, you had, Ahmed, you had something? Okay, yeah. Yeah.
So जिस तरह आपने स्टीयरिंग व्हील वाला एग्जांपल दी थी, तो उसी तरह इफ़ यू डोंट स्टीयर द स्टीयरिंग व्हील, सीधा जाते रहेंगे तो वो पैरेलल ट्रांसपोर्ट होगा.
But how will I know that I have transported it parallelly? So I get the answer over here, that if that a vector is transported parallelly, if the covariant derivative vanishes. So, by definition, I don't like parallelly, but unfortunately I've written it that way. It's not good English. Is by definition, parallel transport means a vector is moved along a path and d of that is equal to 0. Every component of that is equal to 0. So that is the definition. Okay, now let's see the strange things that this leads to if you are on a sphere. So what did we find just a little while ago? That if you are on a geodesic, then if you just follow the geodesic, your vector will be your tangent vector will be transported parallelly. Do we know the geodesics of a sphere? The great circles. we had earlier established that. We had solved the geodesic equation, and we found after some effort that if you move on a great circle, then you're going on a geodesic. So let's move on a geodesic. Okay. So at the equator, here is our sphere. We could start on any point of the equator, but let's start over here. We'll move in this direction. Is this a geodesic? Yes, of course, it's the equator. So we go from here to here. And then, of course, there's a geodesic which is crossing this point, and that also passes through the North Pole. So we move along there. And this was 90 degrees. And then again, this was 90 degrees. And suppose we go 1/4 of the way around the sphere. Then we come over here. This will also, of course, if we go just a little bit off over here and we come over here, then the angle will be a very small one from here to here. But this is 90, this is 90, and this is finite. So on this sphere, the sum of the angles of the triangle is 180 plus something. And this is, this is what Gauss was telling Riemann. I want triangles whose sum of angles is greater than 180. And there it falls out over there. Now, if it was a flat surface, we would get 180, and that's it. So in transporting vectors parallelly, we are, in comparing the initial and the final vectors, we are then looking at something, at a kind of curvature. Now here, it's very expensive, to go from here to here and then there. Let's look for a cheaper way of, the airfare costs a lot. Let's look at a cheaper way of looking at curvature at the point where we are. So suppose I'm sitting in my, suppose we're here in the black hole and we want to know whether the Earth is curved or not. Can we do it? Locally, no? You can. So explain. Explain on the mic.
सर वही ट्रायंगल आप बना के कर सकते हैं. बहुत एक्यूरेट मेजरमेंट लेंगे तो 180 से ज़रा सा बड़ा होगा उसका.
Okay, here I had to travel a huge distance, but I didn't have very accurate measuring instruments. Suppose I'm on a patch over here that is no bigger than the stage, but even over here, in principle, I can find out the curvature if I do the measurements precisely enough. So now I want to show, Zoheb, I want दूसरा लगा दो. So I'm going to transport vectors around a curve. I don't want to draw it myself, so I ask Mathematica to do it. You see how bad my drawing is, so I think this will make it much clearer. Right. Now, instead of me explaining it, can somebody else explain what... यार अंग्रेजी में करना बेहतर है. चलो कुछ भी.
इसमें दो रास्ते हैं ना, एक ब्लू वाला रास्ता है और एक रेड वाला रास्ता है. तो हम पहले ब्लू वाले रास्ते से जाएंगे, पैरेलली ट्रांसपोर्ट वेक्टर को करेंगे, तो उसका जो फाइनल वेक्टर होगा वो VA होगा, जो उस डायरेक्शन से है. फिर हम ब्लू वाले का उधर होगा, वो ऊपर, और फिर हम रेड वाले.
We are taking a vector V.
Yes sir.
The same vector V.
Yes sir, same vector.
But along two different paths.
Okay.
और दूसरे. So tell me which is the first path and what happens on the first path.
Why don't you go to the border?
No, I don't know, because this is going, only this is being broadcast right now. Yeah.
तो जब ब्लू पाथ से जाएंगे तो वो जो VB वेक्टर है वो हम VA वेक्टर जो है वो हमारा VB वेक्टर हमारा फाइनल वेक्टर होगा. जब रेड से जाएंगे तो VA हमारा वेक्टर फाइनल वेक्टर होगा. अगर ये फ्लैट स्पेस होता तब ये VA और VB एक दूसरे से के साथ कंसाइड करते, मतलब पैरेलल हो जाते, बराबर वेक्टर हो जाते. लेकिन ये चूंकि कर्व मैनीफोल्ड है तो इसमें एक डिफरेंस आया है, और ये डिफरेंस जो मेजरमेंट अगर हम कर ले तो ये हमें बताएगा कि स्पेस में कितना कर्वेचर है.
Good. That's exactly what I wanted to hear. Okay. So, but tell me a little bit more. Where are the tangent planes here? Batao. Yeah. Explain a little bit more about this figure. You are very correct, and what you've done is very good, but give me a little more explanation.
P जो पॉइंट है वो हमारा एक उस पॉइंट पर एक टेंजेंट प्लेन डिफाइन है, और दूसरे जो Q पॉइंट है उस पर दूसरा टेंजेंट प्लेन डिफाइन है. तो हम एक टेंजेंट प्लेन से दूसरे टेंजेंट प्लेन तक मूव करते हैं, और उसके लिए हमारे साथ कोवेरिएंट डेरिवेटिव की ज़रूरत होती है.
Okay. Tell me What is the covariant derivative doing? Which have I applied first and which I have applied later?
कोवेरिएंट डेरिवेटिव हम पहले ये ब्लू वाला जो रास्ता है उस पे अप्लाई करेंगे, फिर रेड वाला जो रास्ता है उस पे अप्लाई करेंगे, और फिर दोनों का डिफरेंस लेंगे जिसको हम ली ब्रैकेट कहते हैं.
Okay. Okay, good. So this picture will remain in the back of your mind. And now let's use this to make another very important definition. Okay, so what you saw was we applied first d nu, as you said, to the vector component, to all the vector components, but let's call them v rho, and then did it in the reverse order. And no, it is nice to be to have a shorter notation. So this is the same as and this is non-zero if the space is curved. It is zero if it is flat. But what is it? What is this? It's still a vector, isn't it? यार वो मेरा बंद करना है. Okay. Yeah. We used the reasoning earlier that when you apply the covariant derivative to a vector, then you get a linear combination of vectors. So this will also be a linear combination of vectors. It's going to be a little more complicated. You see, over there, when we applied D to here, we got in general a sum of vectors. Here there's the component, but if this had, you know what I mean, that d mu on V, this was expandable in terms of basis vectors, and this thing is also expandable in terms of basis vectors. So this will be a linear combination of basis vectors, and this is then going to carry the indices of that. Now look over here, if I exchange mu and nu, then this changes sign. So this has to have, this will be anti-symmetric in mu and nu. This I'm going to define. I will use the conventional definition. So this will be sigma mu nu rho, and this will be V sigma. It's got to be linear in V, and this over here is called the Riemann curvature tensor. So when you study general relativity, you really have to know a lot about this tensor, but let's see how many there are. N of these, N of these, N of these, N of these indices. So that's n to the power 4. And in 4 dimensions, that would be 4 to the 4, which is 256. 256 component, my God, what are you going to do with something with 256 component? Fortunately, there are lots of symmetries over here. and I think in 4 dimensions it works out to 40 components. Only 40. What does this tell you? Okay, then you have to, in order to get a feeling for what it is, then you can work it out on a sphere. But this was the motivation here. These two covariant derivatives, they act on a vector and they give back a vector, and this vector is on a tangent plane. And okay, so that's how we define it. Yeah. Yeah. Ugly lecture. Okay, look, you're absolutely right. I haven't defined a tensor. Think of it as a collection of numbers. Okay, it's just like V mu. Think of it as a collection of numbers. But when I write V as V mu E, then I can call this a vector. When I write T as T mu nu, oh sorry, when I write T as T mu nu, E mu E nu, then I will be happy to tell you that this over here is a tensor. So a tensor is a real physical object, just like a vector is a real physical object. But you're right, I haven't yet fully defined tensor, but I'll leave that for the next lecture. We'll need the precise definition because we need to then talk about 1 forms and 2 forms and all that. So leaving that for a while, let's now get some, in the next 10 minutes, get some properties of this. Okay, so this is a fairly ugly object because it's got so many indices in it. Yeah, I'm sorry, you can't avoid it. You have to start from it, but we'd like something simpler. So then comes Ritchie, and Ritchie says that I will take, I'll take the middle index which is now going to be called the Ritchie tensor. So, Ritchie tensor. What does it do? It takes this middle index and makes the upper and the lower the same, contract them as we say. And so this is something that is simpler. So now that you have something that is simpler, well, can you get to something even simpler? And for that, you can do the following. You can take G mu nu and just get something without indices. And that is called curvature. curvature. Okay, now this R is given in terms of these covariant derivatives. Each of these covariant derivatives is of the form partial derivative plus gamma, partial derivative plus gamma, the Christoffel. And so when you will have two partial derivatives when you put that in here, and two gammas or one gamma. Once you do that, then you get the form for the full Riemann tensor, which is then okay, divided by so it's got the right symmetry properties, and I'll write it as R d mu rho nu sigma then is antisymmetric in mu and nu, so d nu plus gamma rho rho mu lambda let's see lambda and then the other way. Four terms, and you can see where they come from because there are two D's over there. So one partial derivative and one Christoffel symbol, and then two Christoffel symbols. And you can see it's quite a mess over here. But you can calculate. Now, suppose we take these Christoffel symbols, which are dg minus dg minus plus dg minus dg. Okay, that's all the stuff over there. If you know g, then you can calculate the Christoffel symbol. If you have calculated that, then you need to take more partial derivatives and work out this mess over here. For a sphere, we already have g mu nu. This was, well, we had g theta theta is r squared and g phi phi r squared sine squared theta. In that case, you see all these mu's and nu's, they will be limited to theta and phi. Okay, you put that in, you work it out, and of course, it's still it's got all these components, and they've been worked out, and you will get R with all the indices, and there are only a few components here. It's all there in the notes. But then the interesting thing is, what does the curvature work out to? Aha. Now here is the problem. I've called this R. And that's the way it is called in the literature. But when you work this out for a sphere, I am using the same symbol r. So let me do this. Let me call this r naught squared. That's a way of saving the situation. Calculate, so to go back, calculate the Christoffel symbols, calculate the Riemann curvature tensor, contract and get the Ricci tensor, contract again and get the curvature. And the answer is that R is equal to 2 over naught squared. What a clear result. You send R naught to infinity, the curvature goes to 0. A big sphere is flat. And yeah.
Earth is a big sphere, so Earth is flat.
Huh? What?
Earth is a big sphere, so Earth is flat.
Locally,
Who says? Are you a flat earther?
Right now.
And it's the wrong question to ask in the black hole, where we live in a very, very curved space. Yeah.
you can say that in this situation, Earth is, smaller curvature in its local vicinity is compared to India, which is something smaller spherical object compared to Earth. We can say it is more flatter in some local.
So the smaller the sphere, the more curved it is. Yeah. Yeah, absolutely. Okay, so we are done. Yeah. One last question.
Sir, when we were talking about the tangents at two different points, can we also say that since tangents at two different points belong to tangent spaces, two different tangent spaces, which are in turn vector spaces, so therefore we cannot add them?
Yes, they belong to different spaces. Exactly. You can add vectors which belong to the same space. In this case, the tangent space here or the tangent space there. But you cannot add the vector in that tangent plane to the vector in this tangent plane. And to know the difference between a vector here and a vector at a slightly different point, then you use the covariant derivative. More in the discussion, and now we'll take a break because we can delay the lunch because